So we want to look at convective mass transfer coefficients. So this is what we want to understand: the mass transfer coefficient as we go to enhance mass transfer rates. So laminar limit, so diffusion in stagnant or laminar fluids is slow. And the industrial goal is to make sure that there is a rapid transfer, as time is always money, and this also minimize equipment sizes and processing time there. So we need to make sure that that is minimized. So how do we do that? If we increase the fluid, if we increase the fluid velocity, we are to move from the laminar region to the turbulent region, where there is a rapid mixing. So turbulence creates edges which will significantly accelerate mass transfer compared to the molecular diffusion. Three regions of turbulent mass transfer. So the viscous sublayer, which is the lamina, and in the viscous sublayer, you need to understand that molecular diffusion is dominant, hence that is going to be very slow. And we look at the buffer transition region. Transport is sum of molecular plus turbulent diffusion there. So this and this is plus the so we all move on to turbulent region. So we have moved quite some distance from the surface. Then transport is primarily via turbulent eddies there. So the molecular diffusion is at its minimum. So classification of convective mass transfer. So we have the single phase transfer. So mass transfer occurs solely within one phase. So moving towards or away from a stationary phase boundary. So this is the sublimation of naphthalene. And the resistance to mass transfer is concentrated entirely within the fluid space. Then case 2 interface, two-phase transfer. So mass transfer occurs simultaneously across two conducting phases. So this is phase 1 and phase 2, and this is the interface boundary there. So it's here it's occurring, here it's also occurring. So gas absorption there, solids moves from a gas to liquid or liquid-liquid extraction as some examples there. So rate of transfer is governed by combined resistance of both phases and the equilibrium at the interface. Turbulent diffusion. Right. So here we want to look at the equation that is given by turbulent diffusion. Remember, equation for molecular diffusion is J equals to minus DAB dCA dZ. And in the turbulent diffusion, we are saying that it's faster and it's enhanced. Hence, the addition of the epsilon of the term EM there. And EM there is mass eddy diffusivity there. Right. So this EM, what's important to understand is this EM at near the surface, it's zero. But it increases as distance from the hole increases. Then we use an average EM bar there, as the variation is basically not known. So from there, 1.61 is written as 1.62 after integrating. So our flux JA1 is based on the surface area. A1, since cross-sectional area may vary. The value of Z2 minus Z1, the distance of the path, is also often unknown. So equation that we saw, 1.62, is simplified and is written using a convective mass transfer coefficient like that. Right. So for easy understanding is so J is equals to DAB CA1 minus CA2. This is all over Z2 minus Z1. Then this is what we are equating to that. There, so experimentally the DAB plus EM is what we are equating to that as indicated there. Is indicated there. Let's look at mass transfer, equimolar counter diffusion, and our equation is indicated there. Then adding the term EM on 1.3133, we are given this equation as indicated in 164. Then when we talk about equimolar counter diffusion, this term, as we had already seen, this term will be equal to 0. So we will simply be left with Kc is equal to this value. And Na is equals to K Ca1 minus Ca. So that mass transfer can be in several ways. So Na is equals to Kc, Kg, Ky, as you can see, depending on whether we are using concentration, partial pressure, and the like. Then liquids, the same applies there. Instead of for the, we have Kc, where we have concentration Kl and Kc. And they can all be related to each other. For example, using equation 1.6 and substituting y there, this is how we can relate the two as indicated there. Hence our Kc is equals to Ky over C. So for a diffusing through stagnant layer there, this is the equation that we'll get there, where we've got Kc over xBm log mean there is indicated by equation 1.610. So those are log means. So this is the equations that we will then use for finding the flux, making use of mass transfer coefficients. So that's for gases. We go to liquids. And the mass transfer coefficients can be related to each other and given as indicated there. So that we can now find the relationship between the mass transfer coefficients as indicated there. And those are the flux equations, the various equations that we have. Thank you.